Okay, folks, good afternoon. This is our session 4, week 2. Just an announcement. Obviously, we have a homework assignment which is due on Tuesday. If you have any questions, please let me know. There are 3 problems there. Starting next week, for only on-campus students, I'm going to take attendance. So starting next week, there's going to be a sheet circulating around, and you have to sign your name. Also, I have uploaded a paper over here, generation and classification of PWM DC to DC converters. I think we will have time today to take a look at it. If not, take a look at it for next time, because we are going to take a look. We are going to actually study the paper. It's a very, very good and useful paper. Any questions? Okay. So what we have done so far, we have looked at the 3 basic and classic DC-DC converters, non-isolated DC-DC converters. The converters are the buck, the boost, and the buck boost topologies. And then we looked at some features that all these converters have in common, like all of them hold a network of switches, switch and a diode that is behaving like a single pole double throw switch. Then there is a pole there, that pole is connected to a stiff current source, which is actually like an inductor. And the throws are connected to a stiff voltages, like a voltage source or a large capacitor or a fuel cell or a solar panel or something like that. We briefly talked about how to simulate these converters, and that's what I'm going to start today. And hopefully we will have time to look at just one isolated DC-DC converter, which is the flyback converter. Okay, so let's take a look at computer simulation. So we are using MATLAB Simulink, or you can use a programming language, or you can use PSPice. There are lots of other softwares available. So let's take a look. So this is my version of simulating the buck converter. I will actually post this on Blackboard. In Simulink. As you can see, I have intentionally tried to use the very basic diagrams and block diagrams in Simulink, like addition, multiplication, division, things like that. I have tried not to use any of those same power tools like a power MOSFET or things like that. So as you can see, you don't really see any switches or diodes over here. I'm going to explain how I got this. And then I have another version of that which has been prepared in Plex. And we will take a look at this one as well, and I will introduce Plex to you guys. And here is what the buck converter actually looks like. So you can actually identify a switch, a diode, a capacitor, an inductor, and things like that. So let's look at some mathematics behind these models and how I got these models. So we are looking at, let's say, simulation, buck converter simulation. The reason that I'm actually using the fundamental Plex, because the fundamental Simulink is, MATLAB and Simulink are basically softwares that are pretty much everywhere. No matter where you end up working with, you will have access to this software, but a lot of toolboxes in there are not available. Like SimPower is a separate tool that you have to purchase, and then Plex is a separate tool that you have to purchase. And your company may not purchase them, so you have to be able to simulate these in the very basic fundamental way of simulating things. All right, so let me see if I can find my note. Okay, so let me draw the diagram of the buck topology. So we have this source. Let's this time, for the sake of variety, use an IGBT. as our switch. Doesn't really matter. All right, don't worry about this diode over here. Sometimes there is a diode, sometimes there is not a diode. It doesn't really make a difference. We don't really use that diode at all. As you can see, we have two actually components that store energy in themselves. One of them is the inductor, the other one is the capacitor. So I can actually start and try to simulate or synthesize this voltage. I usually call this Vx, which is actually the reverse of the voltage drop on your diode. So I can actually say, I think we had it last time as well. So if you look at your notes from before, if you look at the switch signal, or the switching signal, or the gate signal, or the status of the switch, just assume this is a signal that is 1, and the indication is the switch should be on when it is on, and then it is 0, and the indication is the switch should be off, basically. Like a Boolean way of describing the status of the switch: on, or 1, or true, and then off, or 0, or false, something like that. And then we have the input voltage, which is just a constant voltage of Vn, something constant. Then in the end, we are actually building a multiplier over here. If you look at Vx, Vx is the multiplication of these two signals by each other. Or the amplified version of the gate signal, basically. So we have a very simple multiplier. That's why some people call it this an amplifier or a chopper, because we are chopping part of the input voltage out. So my first stage would be I have to generate, I can actually have a square-shaped kind of a source as my gate signal, basically. Let's call it gate signal or switch signal or something like that. And then I can use a constant value of Vn as my constant input source, and I just multiply them by each other. All right, so this would be Vx. Now, if you look at the toolbox, the tools that you have available in Simulink, you have integration and derivation. Try to avoid derivation at all costs, because getting a derivative of a signal is not a very causal way of things. You have to have information about the future value of the signal. If you use derivation, you are going to actually end up with some convergence problems. So I'm trying to basically do integration in a sense that if I focus on just the inductor, I have two fundamental equations, identical equations describing the inductor. One of them is in other words, if I have the current waveform or the current signal of the inductor, I can take the derivative of that and find out what the voltage is, which I'm trying not to use because there's derivation involved. Or if I have the current, if I have the voltage, I can just integrate that and find the current. So lambda is like a dummy character over here. So if I somehow synthesize the voltage drop on my inductor, I can integrate that and then say, okay, the output is the current of the inductor, okay? So let's see what we need to synthesize the voltage of this inductor from here to here. So if you look at this voltage, it is nothing but Vx minus Vout. I already have Vx. I just made it, and then let's say hypothetically, for now, we also happen to have V out, which is the voltage of the capacitor. So I just subtract them from each other. So this gives me the voltage that appears across the terminals of the inductor. And there's a division by any L involved, so I'm just going to do a division. And again, the value of your inductor is just a constant that you can use in Simulink, and then integrate it, which is another block in Simulink. So this would be IL. All right, okay. So now we have managed to basically synthesize or come up with IL, which is this signal over here. Now we have to actually focus on the output side of the topology, the capacitor, the resistor, things like that. So again, hypothetically, assume that we have a current waveform over here. The difference between these two will be the capacitor current. So again, this time I'm closing the loop above. So if I happen to have I out, and I will make it later, if I subtract I out from IL, that gives me IC, the capacitor current. And again, for any capacitor, you know that once you integrate it, you can get the voltage of the capacitor. All right, so we are again trying to avoid derivation. We are trying to use integration. By the way, don't worry about these initial conditions, because these boxes or blocks of 1 over S, or the integration blocks in Simulink, you can double click on them and actually introduce your initial condition. So once I have IC, I can divide it by the value of the cap first. Which is a constant, something like this, and then integrate it. And that would be the capacitor voltage or the output voltage. All right, now we have the output voltage. We needed the output voltage earlier, so I just close it over here. So this is one loop. And then we also need I out. So looking at the topology, I out is nothing but V out divided by R. And this goes back here. So we have two loops. The reason that we have two loops is because we have one inductor and one capacitor. Each one of them is actually associated with a loop. So this is how you can simulate your system using fundamentals basically of the math behind the converter. And then you can add obviously oscilloscopes and stuff like that and basically simulate the entire converter. So what you see here on the screen is exactly what I have over here as my Simulink block. All right, it's the exact same thing. Over here, as you can see, I have this input voltage of 48 volts. The pulse generator, or basically my signal that is applied to the switch, has an amplitude of 1, so it's jumping between 0 and 1. It has a switching period. So remember, for Simulink, you have to introduce the period instead of frequency. So I just do 1 over 100,000. And please do me a favor, when you submit your homework assignment, don't do something like this, for instance. This is my switching period. You have to count the zeros. What was it? You always get confused. Just look at it. Should be easy enough to just look at it and say, okay, my frequency is 100 kilohertz, or my switching period is 10 microseconds. The D is the duty cycle, or the width of this pulse. It has to be in percentage. So pay attention. It has to be 37.5%. It's not points. So if you put this number like this, obviously you're going to get a wrong number, a wrong answer. And there's a phase delay and other features that we don't care about. So you create your Vx over here. You subtract it from the output voltage. You get the voltage of the inductor, division by the value of the inductor, which is here, for instance, 100 micro. Then you do the integration. And this integration block has some initial conditions in case you want to start from a non-zero initial condition, for instance, to save some time. You know that ultimately this is going to land around, I don't know, 10 amperes. So if you put 10, you may actually save some time in terms of simulation. But the simulation is fast anyway. It doesn't really make a big difference. So this is my inductor current. Subtraction from I out gives me the capacitor current, division by the value of the cap, 120 microfarads. And then integration gives me the output voltage, and then division by the load resistance. And I have two values for the load resistance. And I have a manual switch over here. While the simulation is running, I can actually switch from one number to the other in case you're curious about the transient behavior of the system. And then I have an oscilloscope, a probe over here, an oscilloscope, I'm sorry, a probe, which is measuring the pulsating signal. It is measuring the inductor current. It is measuring the output voltage. In case you want to do some high quality plotting, you can actually export the data to your workspace and do other fancy things with it, which we are not going to use right now. All right, so let me run it. I'm running it for 60 milliseconds. All right, so we are done. So a few observations. Obviously, the top signal is a high-frequency signal. If I zoom in, you can see the square shape jumping from 0 and 1. It's not that big a deal. But looking at the second trace, which is the inductor current, and the third trace, which is the output voltage, you're going to observe several things. One, we see some sort of a transient at the beginning. So this is the transient time. Then you reach the steady state. So remember, all of the analysis that we have done so far is only for the steady state. So you have to actually observe the behavior of the system under steady state conditions. The other thing is, if you have taken a control class before, you can see that this behavior resembles a lot like a second order system. And that makes sense because it is a second order system. We have one inductor and one capacitor, second order system. If you zoom in, like the input voltage is 48, the duty cycle is 37.5%. It should give us an output voltage of 18 by our estimation. And you can see that V out over V in equals D for the buck converter is relatively accurate. You can see that this is the output voltage and it is actually hovering around 18 volts. So that's good. Zooming in for the inductor current. It should give me an average. Remember, my load resistance was 10 ohms. So 18 volts of output divided by 10, it should have an average of 1.8. And if I zoom in, you can actually see that. Let me zoom in over here and see what the average value is. It's somewhere around here, which is 1.8. So far, all of our equations are actually making sense. Now, the inductor current is normal, the way we were expecting. It's like a sawtooth waveform ramping up and down. The output voltage is around 18 with a little bit of a ripple. So this is actually the ripple of the output voltage. It's very small, like about 10 millivolts plus or minus, less than plus or minus 10 millivolts. We are in continuous conduction mode, so the design has been a good design if the objective was to operate under continuous conduction mode. So it's pretty much similar to the standard waveforms that we have seen before. Now we can actually mess around. For instance, we can look at the behavior of the system if the load all of a sudden changes from 10 ohms to 2 ohms. So from like a light load to a heavy load. So let's do that, assuming that I'm fast enough to do it. All right. I waited for almost the simulation to get to the middle of the point. That means I have already reached to the steadiest state of 10 ohm resistance load, and then I switched to 2 ohms. So now let's take a look. You can see there is a transition going on over here. You can see, let me just zoom in over here. So before the transition occurs, our output voltage is 18. After that, after the transition settles, it is back to 18. So remember, V out over V in is just D. It is independent of the duty cycle of the load resistance. So right now, I just changed the load resistance. So ideally, you shouldn't see any changes in your output voltage. But remember, our analysis was for the steady state conditions. So here, we were operating under a steady state. V out over V in is 18 or D. And here, again, we get back to the steady state. So again, V out over V in is the duty cycle, which gives you an 18 volts. But then we have a transition for the load. And as you can see also, the inductor current is jumping from one number to the other, because before the step change happens in the load, we are looking at 18 volts divided by 10 ohms, which is 1.8 amperes. Then after that, it should be 18 divided by 2 ohms, which is 9 amperes. You can see this little value over here is 1.8. This value is very close to 10, which is actually 9. So again, our steady state prediction, our steady state analysis can predict before the transition and after the transition is over. It does not predict this transition at all. So this is what we are going to actually study in this class, like small signal models and transition models and things like that. The other thing that you may note is if the load jumps from a light load of 10 ohms to a heavy load of 2 ohms, our output voltage dips. It goes from 18 to a low value of about probably 13.5 or so, and then comes back to 20 and then gradually settles. Now, is this good or bad? We don't know. It depends on the load. It depends on if there are other components connected to the output of this converter. They may not be able to handle the output voltage taking a dip from 18 to, for instance, 13.5 volts. But they might be okay with that. I don't know. It depends on what kind of load you are looking at. So the question is, can we minimize this dip, basically? Or basically, instead of going from 18 to 13.5, what if we could design a controller that would only go from 18 to 17.5 and then recover from there? So that's another thing that we are going to be doing in this class, trying to design compensation networks that minimize the effect of changes in the system, basically.
If the load is dynamic, like DC motors, or does it affect the design of the converter or the control circuit?
So the question is, if the load is a dynamic load, for instance, a DC motor, does that change or affect the power stage design or the controller stage design? I would say probably both. If your load is a dynamic load, what you got to do is you got to make your capacitor a relatively large capacitor to basically eliminate the ripple of the current. At the same time, your controller should be tuned towards those changes so it would be fast enough to respond quickly to the changes in your load. So yeah, I would say both. Any other questions so far? Okay. So now what you can do is you can, for instance, go crazy. For instance, you can say, what if I made a mistake? Instead of putting a 100 microhenry inductor there, I put an inductor that is 10 times larger, like 1,000 micro. Well, obviously, in terms of size doesn't reflect here in my simulation, but if you make your inductor 10 times larger, that means it's going to be actually physically larger. But you can also see that your system is going to get slower. Let's take a look. Maybe not. You can obviously see that the ripple is getting smaller. The peak-to-peak ripple of the inductor current is getting smaller. You can actually see it's much closer. The peak value is only 1.85. Before it was much larger than that. Well, obviously that makes sense. The larger the value of the inductor, the smaller the peak-to-peak ripple of the inductor current. So remember the equation, for instance, for the buck converter is V in minus V out over L times dt. There is a division by L. So if you use a larger L, your peak-to-peak ripple or delta IL is going to get smaller. Other than that, it doesn't really make a difference on the output voltage. We are still hovering around 18. you can see the ripple of the ripple has actually decreased. The reason is because the ripple in the output voltage is caused because of the ripple in the inductor current, and now because this ripple is smaller, therefore the output voltage ripple is also smaller. In terms of the converter being slow, I personally did not observe a lot of sluggishness, but you can argue that from the time that you turn the system on all the way down to you really reach the steady state, because you're using a larger inductor, it takes a longer time to reach the steady state. So you can actually study some trade-offs. One thing that I forgot to mention is, if you look at the transition for the inductor current, it turns out to be negative sometimes. In the previous cases, it was also sometimes negative. This is because we are mathematically modeling things. We don't really have a diode in the system. But if you say in a real buck converter, the inductor current cannot get negative because diode only conducts in one way, in order to eliminate that, you can actually make sure you have a lower limit of 0 for your inductor current. So that means the inductor current cannot get negative. So you actually can see what difference it makes. So now you can see the inductor current doesn't go to the negative areas. It's more realistic, basically. Okay, now let me put this back to 10, 100. And let's say our capacitor is now 10 times larger. Or let's try a 10 times a smaller inductor. Instead of 100 micro, do 10 micro. All right. First thing you notice is the output voltage is not 18 anymore. It's actually larger than 18. It's a red flag to tell you that, okay, all the assumptions that you were making are not correct. The reason is we are not in continuous conduction mode anymore. We are in discontinuous conduction mode. So if you look at the inductor current, you can see that it is in discontinuous conduction mode. So the inductor current starts from 0, ramps up to some peak value, comes back to 0, and then it stays at 0. And so if you choose a very small inductor, you're actually risking going to discontinuous conduction mode, and the equations that we studied, as long as this class is concerned, they are not valid anymore. Your output voltage is not 18 anymore. It gives you a DC output voltage, but it is not 18. So there's another equation predicting that. So let's put this back to 10, 100. And now let's play around with your capacitor value. Okay, let's say your capacitor is too large. Instead of 120 micro, you use 10 times larger. So you can see it actually takes a much longer time for the system to settle. You can see still we are kind of oscillating, and even at the end of my 60 milliseconds of simulation, I have not really reached the steady state yet. So the capacitor is too large. It's very sluggish. It takes forever to get to the steady state. But at the same time, if you look at the output voltage ripple, this is not really the ripple. This little piece is the ripple. Let me see if I can find this ripple. Okay. If you can see the peak-to-peak ripple in the output voltage, you can see it's actually shrunk a lot. Larger capacitor, more sluggish system, but that's a bad thing. At the same time, the good thing is the ripple in the output voltage is smaller, so that's a good thing. What about a smaller capacitor? Let's try a smaller capacitor. Instead of 120, let's make 10 times smaller, only 12. So now you can see the system reaches the steady state very quickly. So it's a very fast system. That's what you want to see, a very quick system. The transition is very short, transition time. Let's look at the ripple in the output voltage. So it's about before, when we had the normal value of 120, I think the ripple was less than plus or minus 10 millivolts. Now it is less than plus or minus 50 millivolts, 5 times larger. So it's up to you or up to the customer. Is this ripple acceptable or not? So there is always trade-off between how well the system functions under steady state conditions versus how quickly the system reaches the steady state conditions. Other than that, the inductor current is pretty much the same, an average value of 1.8, something like that. So let's put it back to the regular value of 120, and now this time let's mess around with the load. Well, I already analyzed this with 10 ohms. Everything was good. We were still in the continuous conduction mode. Let's say we go to very light load of 100 ohms, a load that doesn't consume much power. So you can see your output is not, again, 18 anymore. We are in the discontinuous conduction mode. So light loads cause discontinuous conduction mode, because remember, L was supposed to be greater than something, then multiplied by R. So if R gets too large, L is not greater than expression anymore, and you are in discontinuous conduction mode. And here is how the inductor current would look like. So again, you are in discontinuous conduction mode. Now let's make the load very, very heavy in terms of power consumption. Now let me just do it up here. Instead of 10 ohms, let's make it very small load. For instance, 1 milliohms. All right, something like this. So it's a very small load. It is going to be consuming a lot of power, because remember, output power is V out squared over R. R is too small. Therefore, the output power should be too large. We haven't even reached the steady state, so this might be a huge exaggeration. Let me make it a little bit more realistic. How about 10 milli? All right, we are towards the end. We are getting to the steady state, but the load is actually making the system slow to reach the steady state. But other than that, things are relatively normal. For instance, your output voltage is about 18, okay? And your inductor current has a peak-to-peak ripple of, I don't know, several amps or something like that. But the crazy part is, the abnormal part is, your inductor current on average is about 1800 amperes, which is 18 divided by 10 milliohms. So this simulation doesn't predict. In practice, obviously, you would be smelling the converter right now because it's already burned up. Too much current is passing through the system. So if you short your output voltage, immediately something is going to die in your system. Assuming your power supply it has no protection in it. One piece of advice when you are actually building such a converter, and what students usually do is, let's say they are done, the system is running, they are done, and they basically turn the power supply off. What usually happens, not in the buck converter is okay, but the boost converter, if you turn off your power supply, let me show you a diagram of the boost converter. So usually the complaint that I hear from the student is, my converter was working, I left, I came back tomorrow morning, the day after, and it wasn't working anymore. What happened? So the reason is, usually when you're done with the topology, they just push the button and turn the power supply off. So sometimes what happens is, this goes totally out of the picture. So again, before the converter was functioning, so there was a loop or conduction path for the inductor. You just turn it off. You have actually eliminated that, or you have physically disconnected your source from your converter. The inductor current has to flow through somewhere, and it just creates a huge spark and kills something basically. So if you want to turn something on or off in the lab, I would say, remember, all of the power supplies that we have, they are not like a battery. There's a knob basically. You can start from very low voltages, gradually go up, and when you want to turn it off, do not just push it off. gradually go down. So actually you gradually increase your input voltage to get to, for instance, 48, and then when you are done, gradually reduce it down to 0 and then turn it off. So that is the very first protection measure you can take. Any questions? Yes.
Or what variations in capacitor will push the converter to DCM mode?
Well, okay, the question is what variations in the output capacitor would push the converter into DCM mode. Ideally, it shouldn't do much, but let's try it. Let's try it, see what happens. So remember, the capacitor is in charge of, the size of the capacitor is in charge of establishing a constant output voltage. So if our capacitor is too small, we are violating that assumption. So let's see what happens if we violate that assumption. Let me bring our load to a normal load of, for instance, 10. And then pick a very small capacitor, like in a nano range, like 1,000 times smaller. It is still working, actually, surprisingly. First of all, there is almost no transition at all. Immediately you get to the steady state. But the ripple of the output voltage is too large. So now your output voltage is swinging from 14 volts to 22 volts. But there's still, your inductor current is relatively normal looking. On average, it's about a little bit higher than 1.8 now. But now you can start actually, if you just zoom in your inductor current waveform, it was supposed to be a triangular waveform. I can visually, I don't know, maybe you can actually start that this is actually a second order system kind of a behavior. So instead of being a straight line, that straight line is guaranteed as long as your input voltage is constant, your output voltage is constant. Now our output voltage is not constant. It's actually, as the inductor is getting discharged, my output voltage is going from 22 to almost 14. So here, instead of having a straight line, we have like a second order exponential kind of a thing basically going on. But as you can see, it is still working. It is still working, a little bit deviated from our ideal, expectations, but it is still working, and we have not got to the discontinuous conduction mode. So usually the size of the inductor determines are you in the DCM or not. The size of the capacitor does not drastically determine that. Other questions? Yes.
So will our continuous or discontinuous mode depend upon the D what we take? For example, say buck converter.
Okay.
V output by V input is D. So if you take below 0.1 or above 0.9, will it be a...
Okay, good point. You're right. Okay, so the question is, what about the effect of the duty cycle on going to discontinuous conduction mode or not? So let's look at that. You're right. These will also... So the parameters that are in that equation, remember the equation we're talking about is this equation. What did I do? Okay, this is my office computer. Okay, so let's go here. So this is the equation we are talking about. D is there, R is there, and F is there. Frequency is there as well. So let's mess around with D. Worst case scenario, if your D is a maximum D, this expression gets, if D is a maximum D, this expression gets minimized. No, that's fine actually. L will be greater than that. What about D is a minimum D? This gets too large. Okay, let's try a D minimum. Let's try both. I don't think the design that I have, L is actually much larger than this expression, so it's not going to violate anything. But let's try it. Let's try a very significant small d and a large d. So let me switch this back to 120 micro. And choose a duty cycle of 1%, for instance. All right? So 1% of 48, we would expect to see 480 millivolts in the output voltage. And surprisingly, you do, actually. Well, this is simulation or the design is so good, but usually when you go to very small, excessive amounts of D, the system is going to mess up. But yeah, the output voltage is 480 millivolts, and surprisingly, you are still in continuous conduction mode. Let's do a very excessive large D, like 99%. So your output voltage is still very close to 48 volts. I think it is still again working, so you can see your output voltage is close to 48 and the current is in continuous conduction mode, and the peak, everything makes sense. This is because I've chosen L to be much larger than expression, no matter how D varies. If L is very close to the critical value, then the value of the duty cycle will have an impact. Otherwise, it did not significantly change anything. In practice, you are trying to avoid Ds that are too small or too little, and here is the reason. If you zoom in, you can see if D is large, your switch is almost on all the time, except for a very short period of time over here. Now, is your switch fast enough to turn off and on in that short period of time? So that's the question. So you have a gate driver, you have a switch. Both of them have delay times and transition times. Are they fast enough to turn off and then on in that short period of time? And like in simulation, obviously they do, but in practice, that's the question. If not, that means as if your switch is on all the time. So you are just shorting 48 of input to the 48 of output, something like that. Okay, other questions? All right, yes?
What if we just decide to oversize our capacitor? Let's say we need to choose a particular size of the capacitor for a particular...
So, oversizing is good to an extent. So what we did here, like we chose an inductor which was 10 times larger, and then a capacitor that was 10 times larger. So if you oversize them, several issues. Physically, they are going to be larger, so your converter is going to be bigger and heavier. The other issue is you have to pay more. And the third issue is your system gets sluggish, especially for the capacitors. It took a long time for the system to settle. So there are trade-offs. On one side, your large capacitor guarantees a good DC output voltage, which is great, very small ripple, but the downsides are a sluggishness, large weight and volume, and higher costs. Inductor is almost the same thing. Okay. Other questions? Okay. So this was all about Simulink. Later on, if I'm expecting you to simulate something, I will specify if Simulink-based simulation is acceptable or a Plex-based. So let's look at the Plex-based. In Plex, obviously, you can see your converter. So Plex is, if you have never used Plex before, Plex is, let me see, if you look at Simulink, there should be a Plex somewhere. Here it is. So there are two versions of Plex. One is a standalone kind of a software, meaning that when you run it, you don't actually see that the MATLAB is running. But that is not what I usually use, and please try, especially for distance students and you guys on campus, when I post these files on Blackboard, make sure you can run them. That means you are not using a standalone Plex, because if you email me a standalone Plex because I don't have it on my computer, I will not be able to open it. Plex should be a toolbox in your Simulink. Here is Plex basically. All right. So what happens is this is my Simulink environment, and because everything is under Plex, all you see is just a box of a Plex circuit. However, you can actually import and export, signals in and out to this or from this thing. But let's say we put everything in Plex, and here is Plex. So the background is yellow, and the graphic is a little bit nicer, and you can actually see your converter. And I again put this diode over here, and later on we will see what this diode is. In practice, it does right now, as far as we are concerned, it doesn't really do anything. It's just off all the time. And my input voltage is again 48. My signal is... Now, these are the differences between Plex and Simulink. In Simulink, we had to put the period in. In Plex, you put the frequency in hertz. So pay attention, 100 kilohertz. Duty cycle in Simulink was in percentage, so we had to put 37.5. Here we are, it's in per unit. It should be between 0 and 1, so I'm putting 0.375. Other than that, not a significant difference. There's a diode, inductor, capacitor. An inductor has a little bit of an arrow over there. That means when you're measuring the current of the inductor, because the arrow is directing to the right, that means the current is flowing from right. Positive currents flow from left to right. Capacitor also has a little bit of a positive thing that when you're measuring the voltage, we know what the positive terminal is. If you double click on these components, we can do it today. Well, you can simulate an ideal component. Sometimes when your converter is too busy, if you select everything to be ideal, KVL and KCL may get violated. So sometimes you have to put a little bit of a number there. But right now we are analyzing an ideal converter. So for instance, the on resistance of this FET is 0, and there is thermal issues you can actually play around with. Also for the diode, there is a forward voltage drop on the diode. I'm assuming everything is ideal, so it's 0. In a practical case, it could be like 0.3 volts, 0.4 volts, 0.5 volts, depending on the diode that you're using. You can also determine what is the on resistance of your diode when it is conducting, like 1 milliohms, 10 milliohms, whatever it is. Right now, everything is 0. So you run this. I don't know is it running or not. It says running. Let's look. Yeah. So you can see it's a little bit slower, but it gives you the exact same results. For instance, my load resistance is 10 ohms, so I'm looking at an output voltage of 18 and an inductor current on average of 1.8. And this is the inductor current waveform. So it's a triangular waveform, which I'm used to seeing, and on average it's actually 1.8. One of the great things about Plex is actually the probes, that you can just select like this or this without going and clicking on a button, because in MATLAB you have to click, do I want to do vertical adjustments or horizontal? Here you can just do it automatically, it happens. The output voltage is supposed to be 18. Let's take a look. It is actually 18, and there is a bit of a ripple on it as well, like plus or minus about 5 millivolts or so. All right, pretty much the same results that we saw in MATLAB. I mean, Plex was just a little bit slower. But Plex gives you this opportunity because you actually physically see your capacitors and stuff like that. You can have a better visualization about your circuit. And for instance, if your capacitor has an internal resistance, you can easily add it over here. Or if your MOSFET has some internal resistance of, for instance, 10 milliohms, 10e-3. And your diode has a voltage drop of, for instance, 0.5 volts. So I'm actually stepping into non-idealities in the system. In Simulink, you can do it with some tricks, but here it's much easier. It's just the matter of clicking and changing the numbers. So now let's do it. So now, because my converter is not ideal anymore, there are losses in the system. Output power is not the same as the input power. I'm not expecting my output voltage to reach exactly at 18. As you can see, it's a little bit lower probably. Yeah, it's like around 17.6 volts. This is because we have introduced some non-idealities in the system. But the ripple is almost the same. If you zoom into the ripple, it's almost the same pattern. Instead of being around 18, it's like we have 0.4 volts of voltage drop on our output voltage because of the non-idealities. Pretty much because of the diode. So later on we are going to see that we have to basically close the loop and have a feedback loop that actually adjusts the value of the duty cycle. So the suggestion here is if I just tweak the duty cycle just a little bit higher, instead of 37.5%, maybe 38%, to compensate for the losses in the system, my output voltage grows a little bit to 18, something like that. Well, if you do it manually, you have to run it a few times and see what happens, and then your load changes, then you have to run it a few times again. So a better way would be having a feedback loop, and that's what we're going to be discussing later in this class. Closing the loop so your output voltage is actually regulated at 18 despite the non-ideal effects in the system. And then you can calculate losses and things like that. So Plex is a little bit easier, but just my advice for the rest of your life, use the things that you have already used a lot and you're very familiar with. Do not just drag something in your system. For instance, there was a research group that I was a part of, and one of the students was using PSCAD, and in PSCAD, if you're measuring a signal, there's a gain of 1,000 involved. Like, you read the current is 1 ampere, in practice it's actually 1,000 amperes. And he didn't know about this. So he was running the simulation and his system was unstable, and he would say, yeah, my current is 1 amp, and I don't know why my system is unstable. Then he graduated. I mean, we never realized what was going on. 2 years later, I was looking at the simulation and realized, oh my God, the current was not really 1 ampere, it was 1,000 amperes. So it was 1,000 times larger than what he wanted, and that was causing all the trouble in the system. So please only use the things that are very, very good. And, I click on this, I know all these parameters, the on resistance, the initial conductivity. If you don't know what they are, that means you are not supposed to be using that block diagram. You have to go and study it and then come back and, use it. All right, any questions? All right, so what we are going to do, so this was simulation. Later on, when we get to more advanced topologies, maybe one of your homework assignments is going to be, for instance, simulate a particular converter, later on, but not for next week. Okay, so let's get back to our lecture. So we have covered these classic converters. Now we know how to simulate them in case we are curious about their behavior. There's only one converter that I want to talk about before we get to the main basic topics of this class, and that is the flyback topology. The reason that we are interested in the flyback topology is when we get to power factor correction, sometimes we would use a flyback topology for those applications. So the topologies that we have analyzed so far are non-isolated converters in a sense that, for instance, if you look at the buck converter, the ground of the input is the same as the ground of the output. Sometimes, in terms of protection, this is not allowed. You need some sort of a galvanic isolation from the input side to the output side. So if you have a fault current circulating in the system, the output side and the input side are kind of decoupled from each other. Or sometimes, actually, your input and output do not have the same ground. For instance, let me give you an example. For instance, when you're building a buck converter, as it turns out, you need a gate driver that is a floating gate driver. So let me draw. Let's say we have an IGBT. Okay. The way an IGBT works is if you apply a positive voltage from here to here, from gate to source, the device turns on. If you apply 0, it turns off. So technically you need a pulsating source over there, and you have your main source over here. So you would say, no problem, I will create a DC-DC converter here that takes our source. We already have a source. We don't need to use a second source. And then provides power to this pulsating source. So, for instance, you can say, I don't know, my input voltage is 48, but I only need 5 volts over there, so I can use a buck converter for that DC-DC converter. But the problem is, your DC-DC converter has a ground over here, so it's going to give you another ground over here. That means as if you have actually grounded the source of your transistor, and that's what you want to do basically. So that source is a floating source basically, meaning that this pulsating source over here has nothing to do with this ground over here. So you cannot use a buck or boost or something like that. You got to use an isolated or an isolated converter. So this is one example, and sometimes for the sake of protection, we got to use isolated converters. All right, so let's take a look at isolated converters. Or, yeah, isolated. So as the name suggests, pretty much everywhere or anywhere we want to use isolation, we would use a transformer, right? So let's say what is the most basic converter we can build using a transformer. So, and that's actually called a flyback converter. Obviously, we have many more isolated converters, but we are not going to analyze them. Okay, the flyback topology. All right, so we need some sort of an isolation, so we use a kind of a transformer, or you can call it a coupled inductor. Okay. As you can see, the input side and the output side do not have the same ground, or they are galvanically isolated from each other. The other thing is we are still using one diode and one switch and one capacitor, but the inductor is missing, and as it turns out, we do need an inductor, and the magnetizing inductance of this transformer is actually the inductor that we need. So in some of these isolated applications, the transformer that we are using can provide you the inductor that you need, and sometimes you need to have an extra inductor because that inductor of the transformer is not what you need. The way these windings are wound around this core are important, so there is a little bit of an orientation involved. So what my point is, on the secondary side, we don't have such a thing. The wire is not like this. All right. So this is not what you're using. The wire goes from underneath, then comes up, something like that. So pay attention, that's important. I'm not saying that on the right-hand side you cannot build a boost flyback converter. All you got to do is just put the diode down here then. That's going to be your output voltage, something like that. We are just flipping everything.
It's because the direction of current?
The direction of the flux in the core. So if you have taken electromechanics or something like that as an undergraduate student, you know that we call it a transformer or a coupled inductor. Basically, there's a complicated model involved for these guys that represents the leakage inductance on the primary side, the leakage inductance on the secondary side, leakage resistances, core losses, things like that. We don't use those comprehensive models over here. All we do is we just model this coupled winding with one magnetizing inductance and an ideal transformer. Okay, so let me redraw it now. So now I'm using a circuit model for my coupled inductor. All right, and I'm just going to emphasize on it. So this transformer or the coupled inductor or whatever you name it that we have up there can be modeled using an ideal transformer with turns ratios of N1 and N2, for instance. as well as this red inductor that I drew there, which is the magnetizing inductance. So this magnetizing inductance is not an external component. It is actually internal to your transformer. Okay. So we are going to label a bunch of things, like this is the input current, obviously. And now we have one inductor in our system, so mystery solved. This is the primary side voltage, V1. Secondary side voltage, V2. Pay attention to the dots. On the secondary side, because of the orientation of my winding, actually the dotted node is down there. So the dot is not actually connected to the dotted node. It is connected to the undotted node, basically. What else? So we have a switch over here. We have a diode over here. And obviously you know the rest of the parameters. So if you remember the basic equations for an ideal transformer. First of all, if our ideal transformer only has two windings, one primary, one secondary, we always assume that the current on the secondary is going out of the dotted node and the current on the primary is going into the dotted node. In that case, you can argue that I1 over I2 is N2 over N1. All right, if you assume this convention that I1 is going into the dotted node and I2 is flowing out of the dotted node, you can say I1 over I2 is N2 over N1. And obviously, the other one is the way we label the voltages, which is V1 over V2 is N1 over N2. Okay. And again, when it comes to labeling the voltages, the dotted node gets the positive terminal polarity and the undotted node gets the negative terminal. Okay. So these are the equations that hold for this ideal transformer. An ideal transformer, I've drawn those I1 and I2 and V1 and V2. So anywhere we have V1, you can find out V2, or whenever we have I1 or I2, we can find the other one using these equations. All right. So the classic assumptions that we used to make are still holding, like all the components are ideal. We are analyzing the system under steady state conditions. The output capacitor is large, therefore the ripple in the output voltage is not much, or the output voltage is almost DC, and we saw in simulation it's not that big a deal, we can easily achieve that. And we are analyzing the system under continuous conduction mode. So the current of the magnetizing inductance is continuous. So this is the current we're talking about. And since we have an inductor, I can label this to be VLM. The voltage that appears across the terminals of this imaginary magnetizing inductance. All right. So if you open up some books, sometimes you see that the author has chosen to draw this inductor as a reminder that this inductor is there, but it is not an external component. And some people choose not to draw this inductor because it's not really an external inductor. It's like part of your transformer. So don't get confused when you're opening a book or a paper. Sometimes the inductor is there, sometimes it's not. But in your analysis, there is an imaginary inductor always. Okay, so similar to the previous converters that we have analyzed, we have two modes of operation. Let's look at the first mode. We have turned the switch on, or the switch is closed, and then you have to figure out what happens to the diode. So let's take a look. So if we close the switch, basically what happens is, so I'm actually providing a short circuit path over here. That means I'm actually applying the input voltage across the primary side of the inductor, of the transformer, the ideal transformer. So switch is on. the primary side voltage of the transformer is Vn, the source voltage. Also, we know for any ideal transformer, V1 over V2 is N1 over N2. So we can find V2. Okay, something like this. So why do we find V2? Because then we can write KVL around the loop on the output side and see what kind of voltage appears across the terminals of this diode. Remember, the voltage of a diode always from anode to cathode. And this is the label, this is the polarity that we assume the output voltage has. The top one is positive, the bottom one is negative, then later on we have to verify this. Okay. So once we have V2, I can find the diode voltage. Negative V2, negative V out, that's a KVL thing. So basically the diode voltage is okay. Assuming Vn is positive, V out is positive, and N1 and N2 are integers, so they are positive, they are representing the number of turns. So everything is negative, and therefore this whole thing is negative, and therefore the diode is off. So because the voltage drop is on the diode is off, is negative. Okay. Kind of what we expected, basically. In all of these topologies, you turn the switch on, diode turns off, assuming the designer of the converter or the inventor of the converter has done a good job with their discovery. Anyway, okay. So, so we know what happens to the diode. The diode is off. Technically, that means here there is no current passing, and the capacitor is basically providing some power to the load. I mean, on the input side, whatever is happening, there's no power being transferred to the secondary side. Okay, and as long as the voltage that appears across the terminals of the inductor, you can say the voltage of this magnetizing inductance. By the way, you can assume the magnetizing inductance is on the primary side. You can assume it's on the secondary side. You can say it's divided between the primary side and secondary side. It doesn't really matter. I'm assuming it's on the primary side. So it's Vn. Okay. Now let's look at the second mode, that we open up this switch. Okay. Now that we open up the switch, before we had some current flowing like this. Now we are blocking this switch from conduction. That means this current has to find another path to conduct. So it's going to go here. That's the other path basically, right? So mode 2. The switch is off. Okay. So now let's say, okay, now that the current of the magnetizing inductance, instead of going through the switch, now it's flowing through the primary side of the transformer. So let's see what happens to the diode. So on the secondary, so we have the primary side current now, basically. So all right, so all right, so the current of the primary side, so remember, this is the current of the primary side, flowing from top to bottom. But the current of the magnetizing inductance is the same current flowing from bottom to top, so it's the opposite of, they are the opposite of each other, basically. So I1 is the opposite of ILM, and remember, I1 over I2 is the same as N2 over N1 for the ideal transformer. So we can find I2 to be negative N1 over N2 times ILM. So I2 is negative. What happens to the diode if I2 is negative? Okay, so I2 is negative. So remember I2, which is this current, is opposing ID. Because I2 is flowing from top to bottom, ID is flowing from bottom to top of the secondary side. They are opposing each other. So ID is the opposite of I2 basically. Which is the negative of ID. So ILM is positive, N1 and N2 are integers, they are positive, so totally ID is positive. So there is a possibility for our diode to conduct and conduct a positive current. That makes sense, so the diode turns on. So ID is positive, diode turns on. So again, no surprises here. We turn the switch off, the diode turned on, but it was a little bit more complicated because we had a transformer involved as well. Okay, so now let's take a look. Let's try to see if we can find an expression for the voltage that is applied to the LM, the magnetizing inductance. On the primary side, we cannot find that voltage because the switch is open. But on the secondary side, since the diode is on, in other words, shorted, we can argue that V out and V2 are the same with the negative, basically, polarity. So basically, if I draw the secondary side, this is what we have. So we have a diode that is on, and this was out, V out. So if the diode is on, that means V2 is the opposite of V out. Okay? And remember, again, we have an ideal transformer. V1 over V2 is N1 over N2. So V1 is negative N1 over N2 times the output voltage. And V1 and VLM are the same because they are in parallel. Okay, so remember VLM is the same as V1. I just labeled them differently, otherwise they are representing the same voltage. Okay, they are in parallel. So now you can see we are applying a negative voltage to the magnetizing inductance. So in the first mode, it was positive. In the second mode, it is negative. Again, the classic case of positive, negative, average of 0, so you can find the voltage transfer ratio. So just out of curiosity, what kind of topology is this resembling? Is this resembling a buck boost or a buck boost? Anybody suggestion? Buck boost. So if you look at the table that we had last time, switch was on, Vin is applied, switch is off, something proportional with V out is applied, or negative V out. And buck boost was the only topology. Here actually is the table. Is the only topology that resembles that. So the flyback converter is an isolated version of the buck boost topology. Okay, so on average, VLM should be 0. Therefore, Vn times dt plus should be 0, or V out over V in So this gives us this expression that V out over Vn is N2 over N1 times D over 1 minus D, which again you can see D over 1 minus D appears, which was for the Bach-Busch topology. The extra term that appears is N2 over N1 because we use a transformer, therefore the turns ratio of the transform is also getting engaged in the gain of the system.
Is there a minus?
No, there is no minus. Oh, good point. So if we configure or build the system this way, there is no minus, assuming that this is the positive one and this is the negative one. And also, earlier we assumed that V out was positive here. So that negative V out is negative, and at the end we realize V out is positive. So that assumption makes sense. I think I'm going to stop here. So we are going to work with this just a little bit next time, and then we are going to get actually ready reading that paper that is already posted on Blackboard. So if you have time, take a look at the paper. And there's a homework assignment due on Thursday as well, so on Tuesday. So see you guys on Tuesday.